Hello and welcome back to the course on statistics. Today we're going to take a quick break from running mathematical calculations and we're going to talk about assumptions. Now, we specifically chose not to start this section with assumptions so that we wouldn't get overwhelmed at the start with all too much theory, because we already talked about statistical significance and that was kind of enough for us to get into the world of hypothesis testing and run our first hypothesis test. As you can see, we successfully came up with a result. Well, assumptions are still very important, and it's a good idea to talk about them now so that we are more in tune with what's going on when we're proceeding further with this course. So let's have a look. All right, assumptions of the Z-test, because what we've been doing so far, hypothesis testing, is actually called Z-test or the Z-test. We're running the Z-test because we're looking at the Z-table and we're calculating the Z-score. So the first assumption of the Z-test is that the sample is selected at random. Very important assumption, which often is not taken in the correct manner. And this is, so I'm going to give you like a small overview of what I've seen in my experience and how you can avoid making that mistake. I think it's important to be aware of the possible pitfalls that exist with selecting random samples. It sounds like a very easy thing to do, to select a random sample. Let's look at an example. Let's say you're a government and you want to find out what percentage of your population walks to work, what percentage of your population rides a bicycle, and then what percentage uses public transport, and what percentage drives a car to work. And so what you do is you get a list of people who live in your country, which you might have through a census or something like that. And then you, for instance, you put it into Excel, you add a new column and you put a random variable like a 1 or a 0 and you select 1,000 people at random. So that is a great first step. You have ensured that the way you selected these people are random because you applied a random algorithm. That's great. And a lot of people leave it at that. Okay, we've selected say that we selected a random sample. Okay, here's the sample. Here are the people. Let's look up the phone book. These are the numbers. And then they outsource to an agency to go and call up these 1,000 or 2,000 people to get their insights into how they travel to work. And they think at this stage that that's it. The assumption has been fulfilled. But that's not the case. The thing is that you need to make sure this assumption holds throughout your whole testing process. And I'll give you, we'll extend that example to see what pitfall in this case, the government could have really easily fallen into. And as I mentioned, I've seen this happen before. So what do you normally see in a phone book or in that database that you have phone numbers of? You normally see people's landlines, their home phone landlines. How many people do you know who use a landline, who still have a landline? I'm not sure. I think in the US it's probably even more extreme, but in Australia, it's I know maybe one, maybe two people out of all the people I know who even have a landline. So what do you think the result is going to be when this agency, and the agency usually doesn't really, they do just the job that they've been told to do, that they've been subscribed to do. They don't actually assess the validity of the results and things like that. They just go and call people and check the boxes, and that's it. So what do you think is going to happen? Probably a lot of the people that they call will probably not pick up, and that is usually taken into account. So the government might, provide a larger sample, taking into account that probably, 50% of the people won't pick up or 70% of the people won't pick up. But nevertheless, most of the people that they're going to call through this on their landlines are people who have landlines, are people who still use landline phones. And those are other, I don't know, maybe somebody who works from home, who has a business, who has to have legally a landline, or most likely it's an older demographic, people who still have landlines because they're used to them. For sure, this approach is going to capture a very tiny amount of millennials, a very small amount of people between, what are millennials, 25 to 35 or something, and people, even a very small amount of people, 35 to 45, generation, what is that? Generation Y, I think. So they're going to capture very few people of the more younger population. So the analysis, the sample is going to be skewed towards older demographics. And at the same time, the people who picked out the sample will still be thinking, oh, we selected a random sample. Well, that's not the case, because you did select a random sample, but through the process of your testing, the way you've approached the problem, the sample is no longer random. And the insights that they're going to get back is, let's say they find out that, I don't know, 70% of people drive to work. Well, those insights are not about the whole of the population, let's say of Australia in this case, but they are insight into just the people that this sample represents. So the older demographic, maybe 70% of people over the age of 55 drive to work or wherever they're going, to their hobbies if they're retired. So that is a very important thing to understand, that through the process, just the way you conduct analysis, you might actually skew your sample. And even though you have selected it at random, it is no longer a random sample. It is a biased sample. So there we go. That's about selecting random samples. So be careful of that. Always follow through towards the end and make sure that the sample, that nothing happens that makes the sample become non-random. And a quick question, like a blitz question. What do you think if you called people's mobiles, would that be a random sample? So that's another tricky question. It's already much better than calling landlines, but oftentimes even that's not, it depends on the problem, but oftentimes even that's not a random sample, because when you get the answers, think about it, when you get the answers, your sample represents people who answer questions when called on mobile phones. So, and that's probably not exactly identical to all of the people. So there might be a bias that, for example, more introverted people will not answer a question, even if they're told this is the government or this is a poll or a survey. They might just not answer a question on the phone, or they're less likely. And so therefore, even when you call people on the phone like that, or busy people, for example, businessmen won't have time to answer that question. And so if you call people on their mobile phones, or they might not even pick up. So your sample is biased towards people who pick up their phone and who do answer questions. Maybe that's no big deal for your analysis. Maybe the fact that your sample is biased towards extroverted people rather than introverted people doesn't affect your analysis, because the variable that you're exploring, whether they walk to work or they drive to work, it doesn't depend on whether a person is introverted or extroverted. That's fine. In that case, you can consider this a random sample. But if it does depend on that, for instance, if you're biased towards non-businessmen, for people who do pick up their phone, maybe in that case, it does somehow affect the people that you're excluding, could somehow affect in a different way the variable that you're exploring, and therefore your sample is no longer random. So even in that case, you have to be very, very careful how you select your sample. So you have to think these through. And just increasing the sample size, that's the funny thing here, that just increasing the sample size doesn't solve these problems. If introverted people are not picking up at 1,000-person sample, they're not going to be picking up at 10,000-person sample. I'm not saying introverted people don't pick up, but they're less likely to interact with somebody who's calling them up and asking them about their opinion on something. So hopefully that makes sense, and that's why you have to really think through how you select a sample. Well, that's the easy part, but then how you actually go about ensuring what process you undertake to get the information that you're after. Much easier when you don't have to, when you're dealing like with business processes and things like that, when it's not people that you're dealing with. In those cases, you have a bit more control, and you just go into the business and you get the insights that you need. Maybe you're like surveying parts that are coming out of your manufacturing plant, and you want to see how many of them have defects, how many of them don't. So in that case, it's much easier because it's unbiased. You go and you just look at them. A bit harder when you're dealing with things that are out of your control. Okay, so that was a long note on samples, but hopefully that'll help you avoid some of these very dangerous pitfalls that exist in hypothesis testing. Observations are independent. This one is another very intuitive one. You just have to be careful about it. That, for instance, in terms of surveys and stuff like that, if you go out and, like, it doesn't have to be a government survey. It could be you're surveying your customers. Like, a lot of businesses are B2C, and you might be working in a B2C business, and you might end up working with data like this. For instance, you surveyed your customers and you wanted to find out whether they like your mobile phones that you're producing or not. So what would happen is, how could this be non-independent? Well, let's say you're doing it live. There's like a crowd of people. You're just walking up to them in the street and you're like asking them. Well, when they wouldn't be independent is if you ask like a person and then you ask another person, and the next person hears all of this. So one person says, yes, I love your mobile phones. The next person says, yes, I love your mobile phones. The next person says, yes, I love your mobile phones. And then the fourth person, he is pressured, he feels this peer pressure to say that he does love the mobile phones. Even though his opinion might be different, he might not love them as much, or he might hate them, or whatever. But just because everybody else around him said that, and it's a known fact, this is just the way the human brain works. That we're social creatures, and we are susceptible to. It might be, some might call it peer pressure, but it is a psychological phenomenon. When a lot of people around you do one thing or say one thing, you are more likely to say that same thing. And so when you get to the fourth person, their opinion they're not going to voice their true opinion. They're going to voice a biased opinion, or the opinion that they've just copied of other people, or an altered version of their opinion. And therefore, you're not going to get the true result. And even though it might have been like a random sample and everything else is great, but in this case, your observations are not independent, and you might get an incorrect result. So very important to be careful about that. So hopefully an example that makes this a bit clearer what we're looking out for when we're making sure that our observations are independent. And the third assumption is that the population standard deviation is known, or the sample contains at least 30 observations. So we're going to talk about this more in the further tutorials, but I'll just give you a quick heads up that this first condition, the population standard deviation, is known. As you saw, every time we were running, or time we did run a hypothesis test previously, we knew the standard deviation of the population. We used that to calculate the standard deviation of the sampling distribution. If we don't know the standard deviation of the population, that's also fine, but in that case, we need to run a t-test. It's called a student's. Well, it's based, rather than being based on the normal distribution, it's based on the student's t-distribution, and we'll talk about it. It's not complex at all. You'll see it's very simple. It's another very simple concept. We'll talk about it further down in this course, but in this case, you run a t-test instead of a z-test. And the thing about the 30 sample size here is that in the case when you have 30 observations or more, or the t-distribution is actually very close to a normal distribution. So in this case, it doesn't even matter if you have 30 observations or more. It doesn't matter if you run a t-test or a z-test. It won't matter. It only matters when you have less than 30 observations in your sample. So we'll talk more on that later for sure when we get to the t-test. But for now, those are the assumptions of the z-test. So sample is selected at random, observations are independent, and the population standard deviation is known, or the sample contains 30 observations or more. As you can see, they're very simple, very intuitive assumptions, but at the same time, they can be tricky if you don't look out for them properly throughout your whole experiment. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.